Rogers. Without further ado, David, we have you queued up, I think, for the final presentation today. David's been doing a lot of work already on the Q&A today, but we can't have an event without David speaking as well. So I think he may not need an introduction because many of you who have joined our events have probably had the chance to see him, but I'm fortunate to have him as one of my senior colleagues on the product management team for Spatial Technologies. Tons of expertise. He does it all. He works with customers and partners, and he relays that feedback and works closely in a hands-on manner with our development team to just continually improve our products and services and the direction. And then the fun fact for Roger's benefit is that David actually used to be a drummer in his younger days. So talking about getting the band back together, if you need a drummer, we have David.
Definitely. I'll bring my guitar and vocals.
Cool. So yeah, with that, take it away, David. Thanks.
Cool. Thank you. Thank you, Gene. Thank you, Roger. And I'm going to, Gene, ask you to confirm when you can see my screen.
Looks good. Thanks.
All right. So thanks. Well, first of all, I just want to say personally, I thought that all the sessions today have been really cool, really interesting, and I'm also really glad to be able to sneak in at the tail end here, and appreciate everyone sticking around for the last session of the day. And I'm going to be talking about the ability to take advantage of the features of spatial and spatial data management in Oracle database in general, Oracle Autonomous Database in particular, with Python. So without further ado, just to jump in, because of the fact that this is a Oracle Analytics and Data user community with generally existing experience and knowledge of spatial, I don't think it's necessary to talk too much about what spatial is, but I want to make sure that the context is really clear as I go through this. So of course, what the spatial features of Oracle database are all about is really about being able to treat spatial data as a first-class data type as far as managing, processing, analyzing all forms of geospatial data, and ultimately having that surface in the context of sort of useful exercises, whether it's actual like business applications or in the scenario that we're going to look at today, machine learning and sort of predictive modeling exercises. But what we want to do in spatial is to be able to scale and operate on spatial data within the mainstream of Oracle database. And with that, of course, folks know that we have a native spatial data type, native spatial index, and I just have a bit of an eye chart, just a quick screen grab from the spatial documentation. We have a mountain of spatial APIs and operators and PL SQL packages that handle all kinds of spatial analysis and processing in the database, essentially to be able to manage all different kinds of spatial data, ask all kinds of questions about spatial data. Now, where that sort of veers a little bit for the rest of this presentation is that what all these packages and all these capabilities have to do with is generally being able to have spatial data in the database and to be able to ask spatial questions and most importantly, form relationships or relate data based on spatial relationships, proximity and containment, and which things are near other things. And those are sort of explicit analyses and operations that spatial does really, really well, in addition to just being able to scale and secure and manage spatial data. So that if we go from that to this ML context, I just want to introduce that transition. And a lot of what we saw earlier in the sessions, especially I'll say like maybe Jim's session showing Spatial Studio, he was doing all kinds of proximity analyses and essentially using Studio and Apex to run spatial queries to answer specific questions. Now, what I'm talking about when we move into the machine learning realm really has two dimensions, and I just want to provide some examples for that. First, for vector data, meaning discrete geospatial entities, points, lines, polygons, and then in a moment, raster data, imagery, satellite imagery, aerial imagery, and so forth. So when it comes to vector data, point, line, polygon data, what we're doing with spatial and what this is about is not just asking basic questions, questions that you know to ask and get an answer to. They're really having models and algorithms be able to find things for you, detect things, identify things that you didn't know even to look for, find patterns, detect relationships that you didn't know how to explicitly search for. ML will find them for you, and then ultimately, in the sort of the space-time sense, look forward in time and try to use historical location relationships to predict future. So those are the sort of the ability to look for and identify things for you is where we sort of make that leap from sort of the basic sorts of spatial analyses and operations that we are pretty all familiar with doing, to letting ML models sort of uncover things for us. And then from the raster perspective, when it comes to imagery, the sort of the three main areas, pretty obvious areas that I would mention here would be first being able to detect specific objects or items in imagery. And I have examples for all these, and I'm not going to read them to you. You can just see, hopefully they're really intuitive examples. But object detection first, where there's specific things that you want to train machine learning to do. And in the case of imagery, it's really deep learning, but you want to train your model to find things in geospatial imagery, and then be able to create a spatial object based on that, like the outline of an oil tank that's been detected in imagery, and create a discrete feature based on that. Similarly with segmentation, where you want to take an entire image and let machine learning and deep learning figure out which portions of that area are natural cover versus man-made cover, or different temperatures or ground conditions, et cetera, et cetera. And then finally, like in the vector sense, when I mentioned time, similarly here, looking at the way things, not the way things necessarily are right now, but how they're changing dynamically over time. And deforestation is a classic example of that. So that's sort of the raster imagery side of ML with spatial. And of course, Oracle Spatial, the spatial platform in Oracle database, and in particular now in Oracle Autonomous Database, has just full robust capabilities to store and manage and perform analysis on both the vector data that I mentioned before and raster data with the GeoRaster feature. So now, although we have those sort of data management, processing, analysis features, what does it look like to start to actually work with some of this, some of these ML concepts with spatial? So the picture that I'm portraying here, I mean, this is what you would do and could do, like right now, this moment, and it's what I'm going to demonstrate in a moment. It's sort of the role that spatial would play in a spatial AI or spatial machine learning scenario. And that is essentially for Oracle Spatial, Oracle Autonomous Database, and the spatial features to provide that traditional function of being the spatial data management platform, as well as being able to do in the machine learning sort of scenario what would be referred to as feature engineering, which essentially for us means doing a bunch of spatial processing to get huge volumes of data that you've scaled out and are working with in spatial, and to be able to do a bunch of sort of work in spatial to distill it and boil it down to a bunch of what ML, what the machine learning language would characterize as features that you want to use for predictive models. So there's a whole bunch of sort of upfront data preparation and sort of building and engineering the spatial data for ML that happens in spatial. And then there is also a incredibly sort of vast, wide and deep, I'll say, ecosystem of spatial AI and machine learning modules and libraries and toolkits that handle all kinds of sort of general and specialized areas. the kinds of things that I just mentioned a moment ago. So those sorts of things like detecting patterns and trends in vector data and object detection and so forth in raster data. And so to put those things together turns out to be quite straightforward, harnessing the strengths of both of those. So all of those libraries in and of themselves are not spatial data management platforms with all the scaling and security and parallelism to be able to take huge volumes of data and do the work you need to do to distill it to the things that you want to apply your modeling to. Spatial does that. So within the Python environment, the sort of say like a easy button maybe to be cliche, or a real secret sauce, is the fact that there is this really mature Python driver for Oracle. It used to be called CX Oracle, CX_Oracle. It's now just called the Python Oracle DB driver, or just the Oracle DB driver, that is built and maintained by Oracle, open source, and it just makes it really easy to work in Python, work from a Python notebook, jump into, connect to Oracle, and not only connect to Oracle, but have the ability to natively take advantage of lots of Oracle features without doing extra coding, because that's sort of handling is built into that driver, and to be able to get what you need from it and then combine it with all these various libraries that do all kinds of great stuff. And that's what I'm going to show you. And I just have a bit of another eye chart here, which is just to reinforce the fact that there is so much out there as far as having pretty mature, well-adopted, currently maintained libraries that do all kinds of very specialized things, oftentimes more specialized, than a single vendor is going to build into a product if they're things that are so domain specific, but it's all out there. So I'm going to now shift gears and show you a quick example of all of this. And the environment that I'm going to use to demonstrate this to you is Oracle Cloud Infrastructure, OCI Data Science. And so I want to take one more breath and ask either Gene or Shiva or someone to just confirm that you can still see my screen, since I'm showing something different.
There.
Yeah, we're good.
Good.
All right. So so what I want to show you is really just working with Python and Spatial and some ML libraries to do some interesting, somewhat interesting examples, just to show you how straightforward it is to do all this. I could do that using just Python installed on my desktop or in a container or wherever I choose to, but I'm choosing to use Oracle OCI, the OCI Data Science service, as the place that I do this, just because it's a opportunity to maybe have people just see this if they haven't seen it already. So the OCI Data Science service is a environment that's built for collaborations across teams of data scientists that have lots and lots of notebooks and artifacts and models that they're all sharing and working with together. Clearly not really I'm just have one little sandbox that I'm using for this demo, so it's sort of like killing an anthill with a cannon, to use OCI Data Science just for this. But it just turned out to be a nice environment to be able to show this in and show it everything I'm doing in the Oracle Cloud using native services, the OCI Data Science service and Oracle Autonomous Database. So within the OCI Data Science service, I have created a project which could contain a whole bunch of notebooks, but I just have one notebook in that project, and I'm going to open it up now. And once I do, I've got a session wherein I could create a whole bunch of notebooks. They have sample notebooks and all kinds of artifacts available that I could use as a jumping off point. None of that is really critical to the message I have for you right now, which is really just specifically if you've got Python and you've got an Oracle Autonomous Database, away you go, whether it's here or in your own environment. So I've got a notebook that I'm just going to double click on to open, and then just step through it and explain sort of, the steps, what I'm doing. And hopefully this is something that, anyone could like reproduce exactly what I'm doing really quickly, because it's meant to be a bit of a kind of a hello world exercise. All right, so with that, I'm going to blow this screen up a little to see if I can make this a little easier to see. So maybe either Roger or Gene again, if one of you could just tell me, like, is the text in here big enough to see? I just want to make sure I'm not killing people.
On my screen, so looks good on my screen.
All right,
That's
cool,
good to me.
thanks. All right, so I'm just going to walk through this and give you this basic flow, and it's sort of showing this in sections. And the very first section is just first, I'm in Python. Not ready for any spatial anything, not ready for any ML anything. I just want to create a basic connection to Oracle database as my starting point, and Oracle Autonomous Database in particular. So as my comments say here, and as I mentioned previously, there is this there's this module, open source library, Python Oracle DB, which is the newly renamed Python driver for Oracle database. Couple really cool things about it. Number one, supports Autonomous Database, and as you'll see in a moment, that's what I'm going to be connecting here, to Autonomous Database using a wallet connection. That's awesome. Number two, it now by default uses the new thin driver for Oracle database, which requires no installation of a Oracle client. So that thin driver came out not too long ago, and is now, what this Python driver uses by default, unless you specifically say you don't want to use the thin driver, in which case you'd install the Oracle client and so forth. But it turns out to be just fine. So easy, no client required. It just makes, just connects, and there are limitations. And if any of those limitations are showstoppers, then you have to go ahead and install the client and use the thick driver. The limitation that exists that would be important for some folks like us in Spatial is the fact that that driver does not support object types, and STO geometry is an object type. All that means is that with this driver, you can't select an object type and have that object brought into Python. It doesn't mean that you can't run queries that use an object type back in the database, because when you use this driver and send a query to the database, the driver doesn't care what the query is doing. It just cares about the data types that are coming back. So while on the surface, this might appear like, oh, no object types, Spatial, we need them, forget it. No, it's not the case, because as you'll see, we can do all kinds of stuff with Spatial. All that matters is that what you bring back into Python to work with is supported. And the second important and fortunate thing is that while object types are not supported, LOBs are supported. So that means that we can bring back clobs and blobs. And in particular, we typically in Python, working with all these modules, everyone supports the same common formats like GeoJSON and well-known text. All these libraries support them, as you'll see, because that's what I'm going to use. And Oracle Spatial supports them in terms of just super easy format conversions using functions and built-in methods that make it trivial to be able to specify the format that you want something returned in. So with that said, just using the default thin driver, after all that yakking away, all I do is import Oracle DB. Another cool thing here is the fact that we are going to want to use LOBs, because I want to bring back geometries that might be large, too big for a varchar, too big for a string. I want to bring back a LOB. Normally, by default, when you get back a LOB, a clob from the database, you're actually getting back a clob locator. What's coming back is information about where to find that clob, and then you'd have to make another round trip to go to that location and get it. And we don't want to do that. We don't need multiple round trips. We just want to get the data in one shot. And that used to require, in CX Oracle, it required a little block, a little function, several lines of configuration. Now they've added this really nice simple setting that just says, instead of fetching a lob locator, make that false. Instead, just get the data itself. That's it. One command. Now we're basically completely ready to go. Imported Oracle DB and told it only one round trip, not multiple round trips. So here I'm just simply getting some passwords out of a file just for this demo. And now all I have to do to connect to Oracle database is literally just make this connection pointing to my wallet file and specifying my wallet password. I have a link at the end of this amongst the few links, links that I'll share. There's step-by-step instructions for exactly what you need to load, where you need to put it. It's just, you download your wallet like you were going to connect from SQL Developer or anywhere else, but then you put it somewhere and point to it, and voila, I've created a connection to Oracle Autonomous Database. And I will now create a cursor, which is like a handle on results coming back from that connection. And then I'll just do a hello world query to make sure that I can talk to the database, and hello world comes back. So just select hello world from Dual. So that was it. I'm now connected to Oracle Autonomous Database, and I could start doing queries. So, because love Spatial so much, the first query I'm going to do is just to select the spatial metadata from the schema I'm connected to. So this just tells me, here's the tables, here's the tables that have geometries that I know are indexed. So this is just sort of telling me what I have to work with. And then I want to actually, let's select some spatial data into Python. And so I'm going to just select from a parcels table, the parcel category and the geometry. But instead of just selecting the geometry, because I know it doesn't want to bring back a geometry, I'm going to apply the getGeoJSON method, which is a built-in method that the geometry type has. And so if I run that, I see that I'm getting back the category here, the first field, and then I'm getting back the geometry as GeoJSON. Now, a couple quick things. First of all, the fact that I used this getGeoJSON method is exactly the same as if I had used the utility function that we have, SDO util getGeoJSON, and ran that function to return GeoJSON, and I just used this method instead. And sometimes the method's a little more compact, sometimes using the function makes more sense, but I'm just going to pop over in case people are curious, because there's a bunch of these that are really convenient. And in the documentation here, this is the spatial documentation. If you look in part 1, the concept, this is the Oracle spatial documentation. Under spatial types and metadata, there's the stuff that you're familiar with, like about the geometry type itself, but there's this like little hidden, not hidden, it's right here, section on methods. And these are all methods that you can apply with this dot notation as sort of an alternative to using built-in functions. And in some cases, they do some additional things, but it's really just a different notation that's sometimes convenient. Normally, the default documented approach is to use an alias for the column, and the alternative to that is to surround the geometry column in parentheses, which is what you see that I did here. So that sort of explains this basic query. So what would happen if I just selected the geometry itself? I mean, we know that's not going to be supported, and I don't need the parentheses if all I'm doing is selecting. So if I select a row from this, I'm going to get exactly what I expected, because object types are not supported. But again, that doesn't matter if if what I'm doing is just running queries and getting back results. All that matters is that I bring back things that are allowed by this thin driver. So what about a spatial operation in the database? So let me run now, fetch one row from a query that, instead of just selecting a parcel, selects the buffer of a parcel. So I'm just going to do the exact same thing here, except now the geometry that I'm going to get GeoJSON from is going to be a buffer, like a 100-meter buffer, just to show that, yeah, I mean, this is now just sending a request to the database to do something that involves an object type. But the thin driver doesn't care about that. What it cares about is the fact that it's getting back a clob. It's getting back GeoJSON. And this is the kind of stuff that we can work with super easily across all those modules and libraries in Python. And while I have just a buffer here, in reality, what you're going to do, and what I'll show you, is you can harness all kinds of work in the database for that sort of, I talked about the feature engineering and the heavy lifting and running big parallel queries to do things that'll distill data in a way that is a jumping off point for the modeling that you want to do in with these modules, because you don't want to bring the full, you're not going to bring your geospatial data mart into Python. You're going to bring slices to support modeling exercises. So that's just connect to the database and a hello world and how you can work with spatial data. Now let's just put the database aside for a second and just talk about how you work with spatial data in Python in general, separately from, apart from the Oracle database. So the first thing is there is a library called Shapely, and Shapely is the open source library that provides, like, think of it like a spatial data type in Python. It allows you to handle spatial data like natively in Python. So I'm going to import Shapely, and then for convenience, I'm going to import the well-known text operations, because that's something I'm going to use. That's a format I'm going to use to move data in and out of Shapely geometries. I can bring them back from the database as well-known text, and then Shapely will read that directly. I could have used GeoJSON. So now I've imported Shapely, right? So now what I'm going to do is, here is, in this case, a well-known text, the well-known text that defines the outline of the state of Utah. And I'm going to load that as well-known text to a Shapely object. And then I'm just going to, print and make sure that the type is actually a Shapely geometry, and then show what it looks like. So if I run that, what do you see? Well, yeah, what type is this thing? It's a Shapely geometry that's a polygon. And if you just there's built-in printing that's integrated with Shapely, so that if you just specify the variable name, it just displays a little picture of it. So this is defining a geometry in Python, in this case, explicitly the state of Utah. Now let's do that from the database. So let me get the very first, I'm going to fetch one row from the parcels table. Instead of getting GeoJSON, this time I'm going to get well-known text. And then I'm going to load that well-known text, do exactly what I did before, except instead of defining it explicitly, I'm going to load it from the database. So I run that, and then here is the well-known text that came from the result of the query, and here is the shape of that parcel. So now we've got some data into Python that came from a query of Oracle Spatial. Great, that's just the spatial type in Python. Now, when it comes to not just a spatial type, but actually working with spatial data, like data sets, people working with Python, working with data structures in Python are pretty much all familiar with pandas, which is data structures in Python. GeoPandas extends pandas to the geospatial realm, and in particular takes you from having a data frame in pandas to a geodata frame in GeoPandas. And what that really means is, if you have a geodata frame that has a column, which is a GeoShapely geometry, the Shapely that I just showed, you have a column of Shapely geometries, then that data frame becomes a geodata frame. And then you can do all kinds of fun stuff with it in GeoPandas. So we'll just do that. So I'm going to import GeoPandas, and then I'm going to create a geodata frame. So I'm going to run a query of the database, and as always, I'm not going to bring back geometries. I'm going to bring back well-known text again. I'm going to bring back the first 9 parcels here from the parcels table, and then I'm going to load them into a geodata frame in GeoPandas. So I've done that. Now let's just look at it. I'm going to confirm the type of that geodata frame, and then look at the first few rows of it. So here we go. This is a GeoPandas geodata frame, and here are the columns in that geodata frame. This is essentially just saying, how do I get a bunch of spatial data and get it into a spatial data structure in Python that I would then run with these various models? So now that I've got a geodata frame, there's things I can do with that. Like, for example, I could do a spatial aggregate operation, like create a aggregate convex hull around these shapes. Could I do that in Oracle Spatial? Just do that query in Spatial and bring back the result? Absolutely. But There's also operations that are convenient to do in Python using geodata frames. Maybe some of the data came from Oracle Spatial and some came from some files, and I want to create a sort of a composite geodata frame or set of geodata frames and operate on them. So maybe I want to use Python as the place where I'm exercising some of these spatial operations. So I'm going to run this just to show that here's the result of bringing back parcels from Spatial into Python, and then in Python applying in this case, a spatial aggregation to define the rubber band shape around them. Another thing that we'll need when I get through all this and show you the actual sort of ML part is plotting. So PyPlot has basic built-in plotting, so I can select, in this case, a grid of data and show it. I can select, this is selecting data from the database, select states from the database and show it. And then finally combine them together into one. And now this is and I will finish in 3 minutes, Gene. I know I'm going long. So now the final bit, which is the actual data science scenario. So what I have is, for every grid cell here, I have historical traffic crash data with all kinds of information about the cause of the crash or what the factors of the crash were. And I want to do some spatial ML around detecting things in that data. So I've got this historical crash data, and I want to know specifically for every one of these grid cells, what % of the historical data was due to high speeds. So that's the metric that I want to pull. And what I'm going to show you is I've got attribution here that this came from a sample notebook that from PySal, which is the module that I'm going to load in a moment, that is the spatial data science module with mind-bending width and depth of capabilities. And it's one of their sample notebooks that I've adapted to the data that I have in Autonomous Database to sort of use my data as the scenario. So I'm going to start by creating a geodata frame from an Oracle Spatial query that does the aggregation of historical crash data by doing sort of a spatial join between the crashes in the grid, and then doing a calculation for what % of those crashes are due to speeding. And that's what we have right here. So this is the spatial sort of feature engineering to give me a grid key, a metric, which is for that grid cell, what % of the historical crashes were due to speeding, and then the geometry of that grid cell. That's a geodata frame. So now I just jump into loading the modules that I need from this PySal, which is this spatial ML library. And then I can just start to do a bunch of stuff that I'm going to really skip over because I don't have enough time. So I'm going to skip over some of the data exploration where I just am sort of plotting things based on different ways of classifying the data based on statistical groupings. But what I really want to get to is this last bit here in the last minute. So the specific thing that I'm going to show here is how to find hotspots and cold spots. And that's different than finding clusters. I'm not looking for places where there are lots of crashes. I'm looking for areas that are that have a higher concentration of being related to speeding, or a lower concentration of being related to speeding based on other crashes around it. There may be an equal distribution spatially of crashes, but I'm looking for areas that tend to be high crashes surrounded by high speed crashes, or crashes that weren't high speed surrounded by other crashes that weren't high speed. And that's the kind of stuff. I mean, it's a real hello world example, but that's part of what this provides. So the methodology is to first do what's referred to as creating a spatial weights matrix. And so for every single grid cell, it identifies what are all the surrounding grid cells and gives you a sort of a factor to proportionally weigh all the surrounding values. That can be done in lots of different ways based on different sort of proximity relationships. This is the basic method called the Queen method, where you're taking equal weights from every surrounding grid cell. And then the next thing I do is create sort of do a global calculation that tells me that describes to me the relationship between grid cells and what is surrounding those grid cells. And what I want to know is is that relationship random, or are there spatial trends that are meaningful? And if the data were random, it would be like within this blue bell curve. My data is this red line way out here. It's not random. There are spatial patterns and spatial trends. There's correlation of information at locations with that information in surrounding locations. There is spatial correlation. So what I can then do, now that I know that the data are not random, is that I can apply these built-in methods that for every single grid cell, for every single location, it will tell me, is that grid cell a high value surrounded by high values, or a low value surrounded by low values, or a low value surrounded by high values? It'll give me sort of the context of every location, and then tell me whether the result is statistically significant based on stuff that I don't, we don't have time to get into it because I'm now 2 minutes over, but this is now telling me whether every single spot is a hot spot or a cold spot or an outlier, and whether it's statistically significant. And then what I can do is simply plot all the grid cells and show in the dark color which of the grid cells that are in fact statistically significant hotspots or cold spots. These are the areas that are statistically significant in terms of having high-speed crashes surrounded by high-speed crashes, or not high-speed crashes surrounded by not high-speed crashes. And then from that, I can then determine the hotspots and cold spots. So these in red are the grid cell areas that are characterized as being hotspots, meaning through all this sort of statistical operations that these modules supply, this is what I could defend as being areas where there is a higher trend in high-speed crashes, or crashes being associated with high speed. And similarly, this would be the area that are cold spots, meaning there tend to be crashes not related to high speed surrounded by others. And this, of course, would be sort of the starting point for a deeper look into, okay, what's common amongst the areas where high speed's a factor? What are the sort of maybe the driving, regulations, or the road conditions, or the demographics, and lots and lots of things. So this would then feed into, but the point is that this is one pretty basic, specific example of using spatial to do the feature engineering and scaling and accessing the data, and being able to run with it in Python to apply various machine learning algorithms. And so to conclude here, there are a bunch of resources that are in the deck that everyone will have access to. And I also want to mention like two other quick things. First of all, that picture of Oracle Spatial providing the spatial data management, analysis, processing, and Python libraries, open source libraries providing all the ML. That's our picture right now. Our roadmap and sort of our active engineering includes a bunch of work on changing that picture in a pretty substantial way, so that you can look forward you can look forward to seeing a whole bunch of new and exciting spatial AI and spatial ML sort of being part of what we will deliver, and something that will be the subject of future sessions like this. And then finally, with the upcoming Cloud World, I want to encourage everyone that can go. And if you just go to the session catalog for Cloud World and plug in Spatial, which you see on the left, and Graph, which you see on the right, there's a whole bunch of pretty interesting sessions, like full learning sessions, lightning talks, and hands-on labs, workshops to participate in. And Jean, I'm going to hand it back to you.
Excellent. Thanks so much, David. And your presentations always deliver so much value for the money and the time. So that was really awesome. That was great. So yeah, I think we're at time. I don't see any remaining questions in the Q&A, so I think we're good on that.